you? So obviously I will be late every time because I go to the gym and I come here, I will be late. So from now on, can we do 10:30 to 12:10? Basically no break, okay? And if you need to use the toilet, drink water, you can just come out or go out to the classroom. That's fine. Okay, so from now on, Tuesday morning, I will be late because I go to the gym earlier than this, and traffic is going to be making me 10 minutes late. So I think if we don't do a break, then we're fine. I give you the same amount of the lecture. Okay. So basically today and tomorrow we are going to cover a review of mechanics of materials. I think I can. Okay, so you know about this. Every material under a certain kind of load, there could be stress inside the material. And in a mechanical component, the stress everywhere is different. And the important thing about this lecture is to find out along which direction this material, this particular element is carrying the largest load. Why do we care about the largest load? Because safety factor is a ratio between the strength over the largest stress. Okay, so let's say the strength, like your muscle, if your strength is weaker than the load, then you're gonna break your muscle. If you are strong enough, if the strength is certain number of times stronger than the largest load you're carrying, then the material won't break. So as a mechanical designer, we need to figure out what's the maximum stress this material is carrying along certain direction, and also how many times our strength is greater than our stress. So you can even make certain proper design of your safety factor, because you don't want your mechanical component to be too strong. Usually if you have more material, it's gonna be stronger. However, it's gonna be heavier, it's gonna be more costly, more energy wasting. So strong is not the best. So just enough would be the best, because that would be the most effective way to design a mechanical component. And basically, if you forget, I think you should remember this. You have normal stresses along the axes. If you have a XYZ coordinate, basically the way you define your coordinate defines how you are going to express the orientation of your stresses. You can view this material in a different orientation than your XYZ is lying along a totally different direction. Then you are basically viewing this particular point in a different way, different orientation. Then the normal stress in that new coordinate will not be lying on the same direction. So what I mean is, if you rotate your coordinate in this direction, let's say this is x prime, this is y prime, and this is z prime. And usually when we draw a box, doesn't mean the element is a box. It's actually a dot. It's a small point. So when you view this exact same point inside the material in a different orientation, x prime, y prime, and z prime, you are basically tilting your head and trying to view it in a different way. In that case, when you try to exaggerate the shape of the point, in that new orientation, you are exaggerating that shape in a different geometry. So that doesn't mean you are rotating the box. It's just how the box is just to help you visualize which plane a stress is lying or perpendicular to. Okay, so when you see something like this, it only means you change the orientation of your eyes. Okay, the element is still a dot. Okay, so I hope you get what I mean. Okay, so later on, when you have like a planar stresses, they are shear stresses. So the first index represent the location of it, and the second index represent the direction of it. Like this particular one, sigma zx, it lies on this plane that is facing z direction, and then the vector is pointing toward x, so zx. Okay, it's just a quick review. I think you know this. Okay, very simple. Now, for material, we are in this course. We are mainly focusing on elastic mechanics. So we don't want our mechanical component to pass the yielding point, because it's gonna break, or it's gonna deform permanently, and we can never use it anymore. So the goal of this course is trying to design within this linear mechanics region. We never want our design to reach the yielding and permanently change its shape. Okay, that's why we care more about elasticity. Now, just a quick reminder about the symbols and the terms. Sigma is stress, epsilon is strain, E is Young's modulus. They are having this linear relationship. Basically, it's describing this linear region, the linear relationship between the stress and strain. Okay. By definition, stress is the load over the stress area. Okay. Strain is the amount of your deflection over its original length. Okay. And due to this linear relationship between the sigma and epsilon, you can combine three equations into this new form, and at the end you can compute for this delta, the deflection. So the deflection depends on the stress you apply, original length, and also at the bottom you have the material property Young's modulus and the area, how thick your material is. And over here, at this critical point, yielding point, this is the point where your material is about to change its shape permanently. So the stress right here basically is called the yielding stress. So later on, we have many design models. We try to avoid our material to reach the yielding strength. Okay, and if you have done tensile test in the past, you can continue to pull the material, and then at some point there is a extreme, ultimate, maximum stress point. It's called the optimal tensile stress. In this, in my notes, we use sigma u. Sometimes I use YP for yielding point, UT for ultimate tensile stress. And there is a compression stress, but we mostly focus on the tensile stress. Okay? So we do use these two values later on in some of our design equations. Okay? Just for you to know. So far, it's very simple. It's like what you have learned several years ago. Now, let's talk about a beam problem. Bending. So this is pure bending. If you purely bend a beam, everywhere inside the beam, you will have normal stresses. Okay? So over here, because it's like you are bending the beam in this way, and right in the middle there is a neutral plane. There will be no deformation, but everything above is gonna be lengthened, and everything below is going to be compressed. Okay, so in the tension part, it's carrying stress that is like pulling the material away. So it's like being pulled. And at the bottom is being compressed. Okay? And since we are following linear stress region, linear mechanics, so we can easily assume the stress inside is following some kind of linear relationship. And since right here we know this should be somewhere you have zero stress, and here you have positive stress, and here you have negative stress. So you can easily assume there will be some kind of linear model like this. It's just that you don't know, at this point, you don't know the relationship between the amount of the stress and also the distance right here. Okay, if you call this C, right? There is gonna be some kind of relationship between the distance and the amount of stress. Okay, so the goal next is to compute what would be the model right there. Then you will know the stress everywhere. If you know the linear equation right here. Then later on, if you would like to study somewhere right here, okay, at this particular height, how much tensile stress you are having. Let's say this is X. You want to know, okay, this should not be X because this is X direction. If you say this is some value Y, you want to know, okay, what is the sigma Y right there? Then follow that linear equation, you can compute for it. Okay, you can know the stress everywhere. Okay, everyone good? If you, at some point, if you feel like I'm doing this too fast, you can let me know. Okay, and since the stress is caused by the bending moment from the outside, so there should be some kind of relationship between the stress and the moment. So important term right here is the position you're studying. So let's say this is some value Y, and the magnitude of the stress at that particular height, and how much this is related to this. So there will be some kind of relationship that you should be interested in. So the goal next is to compute for that. Okay? Everyone okay? Too easy? Yeah, it is supposed to be easy at this point. Now, here's how. This is what I have drawn. Position of y, and you know the stress is gonna be sometimes some value times the position of y, because it's a linear relationship. So we assume coefficient k right there, but we need to compute for k. Okay, we need to compute for that. And how do we do that? We are going to use balance of moment. So how do you do balance of moment? So we are going to focus on this particular area, this small area. So at this small area, if you view from the side, there is a stress area right there. Okay, so it's like a small increment of y. Okay, and right there, the width is b. So this small area is gonna be b times dy, right? So on that particular small area, we're going to figure out how much stress is being applied on top of that small area. And it's already here. It's k and y. So how much force is being applied on that particular area? We know the relationship between the stress and area and force, right? So if you do this is stress times area. This is force, right? Stress is force over area. So stress times area is force. And this term basically is the total force being applied on this particular small area. Total force. Only on this thin, like a strip, rectangular area. And that much of the force is gonna generate some kind of moment. And where's the rotational center? It's like the center is right there. So what would be the radius for that moment? It's gonna be y. So the force right here, so there will be some kind of force multiplying this radius is contributing some kind of moment, right? So this y is the radius. So after the force multiplying y, this would be moment. But this is only the moment contributed by the small portion of the force being applied on this red area. So how can we compute for the total moment that is generated by the stress? We can sum them up. But since we are only focusing on a small increment of area, how do we sum? This dy is super small. So the way to sum all the area is to do integral. So that's why there's an integral. But when we do integral, where are we doing, what's the range? We are taking the integral from here to here, from the bottom to the top. So at the bottom, what is the value of y? Y equals to negative c, right here, negative c. Okay? To the top, y equals to positive c. So on the right-hand side of the equation, that's the total moment generated by the stress. And that's gonna be balanced by the moment you apply right here. So in this particular force diagram, this moment by your hand and the moment that is inside the material, balance out. Okay, so what's next is math. Okay, so now let's try to apply some math. Sigma equals ky, just apply into it. So there will be a ky squared and dA right there. Okay, so we know k is just a coefficient. It has nothing to do with your position y. So it's a constant, remains constant inside the entire integral. So k can be taken out. So after you take k out of the integral, you can get the following equation: k equals to m over this particular term, the y squared dA. And this term is basically the area moment of inertia. You may have heard of it, okay? From many solid mechanics book, or you can Google for internet. They have area moment of inertia for different shapes. And the most popular shape that we deal with is rectangular one. So there is Ix and Iy. Okay, basically it's the result of this particular integral. So now I want to remind you what is Ix and Iy. Right there, I have proven what Iy is exactly the same as the one taken from the textbook. So this is just a proof. Exactly the same integral right here. So you can take a look at how it's proven on the right hand side if you're interested. So the key is when you take a look at the information like here, you see a picture like this. What's the difference between Ix and Iy? So the way I try to memorize it is Ix and Iy is going to be utilized for stress analysis and utilized for bending. And when you bend, you are bending about certain neutral plane or neutral axis. So here is your neutral axis. You are bending this way, right? Or on the other side. So you're bending this way. This is your neutral axis. So from the side, on the cross section, you are bending about a certain line. So it's like you are bending about x axis. You are bending about it. Okay. So the value you are going to take is gonna be the Ix. Because right here, see, I proven we need to use this one, we need to use this one, and this is basically bending about x-axis, okay? So that's easier for you. Later on, you see a picture like this, and you see, oh, Ix, should I take Ix or Iy? Then you just try to figure out what the problem is about. Is it bending about x-axis or bending about y-axis? Then you will need to take the right one. Okay? So that's how you get I. Once you have I, you know how much moment you apply to the beam, and you know the position where the plane that you are investigating. Then you can study for the stress anywhere you are studying. Stress at any height of what? Okay? Everyone okay? We are moving very fast, but this is all you already know, supposedly. Any question? Anything you forget about? Everyone have learned this, right? Who haven't learned this in the past? Everyone learned this, yeah. So this course should be pretty easy for you. Okay. Now, what's next? We have another kind of stress, but now it's applying on top of a linear object in a different way. We are going to twist it instead of bending it. So this is pure twisting. So for easier analysis, when we twist it, we would like to study on top of a cylindrical object, because everywhere about the central axis is axisymmetric. Since for a cylindrical object it's axisymmetric, I can easily use those derivations to compute for some general solutions. Okay, that's why in the previous page we are studying for rectangular cross-section, because it's easier for bending problems. But for cylindrical objects, if you are studying for twisting, cylindrical objects is easier for analysis. Okay. Now, what do we do? Basically, you are like twisting a towel, like you are drying the towel. Okay. So you apply certain torque. Okay, from at both ends, okay, but different direction. So imagine you have a point right here that is fixed, and you draw a dashed line from here to the other edge, and this line is being drawn along the axis. After this is being exaggerated, after the cylindrical object is being twisted, that particular line is being twisted like this, and this particular angle is the basically is the string. Okay, so that angle is like the angular deformation. Okay, in the linear stress analysis, you have sigma for string, but for twisting, your string is studied in the angle, in the degree of angle, in the unit of angle. Okay, so you can compare. For linear equations, it's like this, right? This is linear stress. This is like a shear stress, and this is Young's modulus, and this is shear modulus, and this is linear strength. This is like a angular strength. Okay, so they kind of match in a certain format, but totally different orientation. Okay. Now, we need to study certain geometry so that we can figure out the stress inside and how the stress is generating certain twisting moment, and how those moment is being balanced by the torque. So similar calculation, also using the trick of taking integrals. But now we're doing this in a polar coordinate. Now, we would like to focus on particular radius on this particular radius. So at this particular radius R, since this is axisymmetric, so the stress level on this particular radius is exactly the same. So right at the middle, we have zero shear stress. As the radius increases, you have more torque generated by the shearing force. So we can assume the shear stress should be linearly proportional to the radius. So the only thing is what's the linear relationship? So there's an unknown k right there. Now, right here at radius r, you have the tau r equals to kr. So we define in this way. And this tau is applied on this ring. We basically we would like to study the stress everywhere on this ring. So the stress area is the entire ring with super thin width. So this width is going to be dr. Okay, so what would be the area of dA? So we will later on figure out. Okay, so there's a dA right here. So the centric, the shearing stress along the tangent directions everywhere, multiplying the area. So this is stress, multiplying area. This is again, this is the shearing force. And what's the direction of the shearing force? Basically like a tangent everywhere. Okay. On top of the ring, the amplitude is tau times dA, but it's the same everywhere. And those shearing forces multiplying the radius, you end up with how much torque is being generated by the shearing forces on the ring. So this is the torque due to the shearing force. But you need to sum them up. That's why you take an integral from r equals to 0 to r equals to capitalized R. So this is small r equals to 0 to integral to capitalized R. Okay? Now, since we have the model capitalized K, R, we apply it to the equation. We have this capitalized K, R squared dA. And again, capitalized K is a constant. It has nothing to do with the radius or area. So it's a constant inside the integral. You can take it out. And then you come up with this K equals to this particular equation. And at the bottom, this one is the polar area of inertia. Area moment of inertia. Okay, so usually there's a symbol called J, or sometimes they will use IZZ, that equals to IXX plus IYY. Or sometimes they just use IZ, so equals to IX plus IY. Okay? So earlier in the previous slide, there's calculation of IX and IY. How do you compute J? You just sum IX and IY. That gives you J. Okay? Now, so you can then apply this K back to the tau equals to KR, so you end up with this tau equals to TR over J. you end up with that equation. Okay? And over here, just for you to know, you can even compute for this particular theta, this angle, theta. Okay, so it's like how much angle of twisting you have when you view from the side. Okay, how do you compute for that? That relies on a calculation of r theta equals to L gamma. What is that? Basically, this is the arc length right here. Arc length. So arc length equals to radius times theta, right? So over here, r times theta. Also equals to radius times theta. So also equals to L times gamma. But this is only valid when the deformation is very small. Okay, usually for metal, when you twist it, you cannot twist too much. So it's actually an exaggeration on the drawing. Okay? If you have this equation, you then can formulate the following. You know theta equals to this guy, and then you can apply the tau over here. So at the end, theta equals to how much torque you apply, what's the length of your beam, what's the shear module, material property, and J. So J is a property that depends on the cross section, the shape, okay. The polar area moment of inertia. Okay? So this is a very fundamental stress analysis for bending and twisting. Okay? Let's continue. Now, for a shaft, we already know sigma equals to mr over I, tau equals to tr over j. So we can truly apply the equations into these two equations. So from the textbook, for circular geometry, Ix, Iy, Iz can be determined on the right hand side. So let's plug in at the bottom of the first equation and the second equation on the left. Plugging on the bottom part. And this time we would like to convert radius to diameter. We like to design in diameters. So we change all the r into small d. So at the end, after the derivation, for a shaft, basically circular cross-section, basically for pure bending, you have sigma equals to 32m over pi d cubed. And your shear stress for pure twisting, tau equals to 16 t over pi d cubed. So please memorize these two equations, because you are going to use it multiple times in the future exam. Okay. Please memorize them. Now, this is just a proof for area moment of inertia. I think I'm gonna skip it. Just a proof. If you are interested, you can come back and take a look at the proof. I'm not going to use the lecture time to prove it. So, for comparison, I think I did the comparison already. I'm gonna move on. So, let's already talk about shape problem with pure bending plus pure twisting. Okay? So, we are actually dealing with plane stress problems. So let me explain why we are working on plane stress problems. So when you bend your shaft in this way, like up to down, then over here on top it's being pulled, right? But for the material on the side, here is neutral. Here is no stress on the side. Okay? Now, since you are also twisting the material, so it's like the material is being twisted. Oh, okay, so on this material, on its side is being like pushed that way. So if you look at the top right here, it's being twisted, and here is being pushed downward. And you know, for shearing stress, it always comes as a couple. So since there is shearing stress up, like this is clockwise, and here this one is also clockwise. So on the other side, you will have opposite shearing stress. So actually, here is a shearing stress going left if you view from the top, and then going right if you view from the top. So if your eyeball is right here, this is your eyeball, and you are eyeballing this particular element from the top to the bottom, viewing this material, then this particular material looks like that. Okay? And because of the bending and twisting, the stresses are only applied on that particular XZ plane. You don't see any additional stress along the Y direction. In this particular drawing, along the third direction, there's no stress. That's why it's called a planar problem. Okay? So this is actually a plane stress problem. So the third, I better not use this one. The third dimensional stress equals to 0. So that's a plane stress problem. If in the future you see the strain along the third direction equals to 0, then it's a plane strain problem. No matter you are doing a plane stress or plane strain problem, they are planar problems. So the way you solve them is basically the same. Okay? And how about the element from the side? Because the twisting is applied everywhere, so over here you still have this twist, going left and going right. So if you view this material from here, from the left, viewing the material, then you will see it has only twisting. Okay? So what we will be interested in next is a planar stress problem, but can we view this particular material in a different orientation, not exactly along the XZ direction, so that we will find out the stress is actually larger. That's basically the principal stress analysis. So basically, we're doing the Mohr circle. Okay? So the next will be Mohr circle analysis. Okay? We need that. Because we need to find out, can we view this element in a different way? Then we realize, if I view this material in this way, the stress is actually the largest. Because at the beginning, we already said, we need to figure out what's the largest stress being applied to this particular material. We don't even care about the stress that is weaker. We only care about the largest. Okay? So, now we are moving on to principal stress. Okay. Oh, this slide is finished. I need to download my second slide. Second slide is here. Okay. Let's talk about Mohr circle first, and then we talk about deflection. So this is about deflection. We'll talk about deflection later. We'll talk about this. So in this particular problem, the same problem, we are focusing on the material on the top. And we already have this force diagram on the right-hand side, right? We know the stress, normal stress equals to 32 m over pi d cubed. That's why point B is here, okay? The point B is that B point here represent the stress condition right there. And if you move on to point C, you realize the stress condition on point C is actually the same as point A. It's just that you have turned your observation point by 180 degrees on the material. But over here on the Mohr circle, you have turned 360 degrees back to the point A. So supposedly in a material, the stress condition should be quite continuous. So the way we observe the stress, we can actually, if we have some kind of stress meter, and we can take a walk from point A and then along the same radius and then continue to move about the center point and then walk toward point C, we will be taking a 180 degree turn from the right to the left. But for the stress condition, it's gonna be some stress condition A, and then it's gonna make a circle and move to point B. That's where you will have B point here, and then continue to make a circle to go back to the original point. So when you turn 80 degree here, you turn 360 degree on the right. That's why Mohr circle is like having a circular shape. And we can use some of the stress conditions on the positions that we know to get certain points. And with the information of certain points, we can already draw a circle. Okay. Now, if we can draw a circle, we realize, and somewhere right here, it's actually carrying the largest normal stress, but no shear stress. So when we walk to certain position on the left, the stress position actually moves to this particular position, and that is the observation point where is carrying the largest load. So this is what we're looking for. We would like to know the amount of the extreme stress and also where exactly that is. So how do we do that? So right here, if we change the way we observe this, if we rotate the coordinate about this center by theta right here, and if it turns out on the Mohr circle, I will be making a 2 theta angle of rotation. And if that observation point moves to this particular point, then you know when you observe in this way, actually, this element is carrying the largest normal stress. So in fact, in this particular problem at the beginning, on this particular point, there is a larger stress actually like this. So this is a first principle stress. So there is a stress over here, but it's not along any direction. It's not along x, it's not along z, not along y, but we want to know along which direction. Okay? So that's why we need the Mohr circle analysis. Okay, like this. Okay? So now we know this S represents the principal stress. This is the first principal stress. Okay? And if we, from there, from this particular point, if we turn 90 degrees again up to this point E, on the Mohr circle, we will be turning 180 degrees. Then we reach to this E point on the Mohr circle, the very left. So this is the largest compression stress. This material is being applied. So right here, when we observe this element in this orientation, up and down is being compressed. Okay? So that's the second principal stress. Is there a third principal stress? Yes. It's along the third direction, but now it's 0 because we are solving a planar problem. Okay, and there's another direction that we are very interested in, is where we take a 45-degree turn from the principal stress axis. We take a 45-degree turn from here. So on the Mohr circle, we will be taking a 90-degree turn. And right here at the point F, that's where we have the maximum shear stress. So it's again, we are observing this way, but now we turn 45 degrees like here. This is where we have the largest shear stress. Does that mean at this particular orientation we have no normal? Not necessarily. Right here we still have this amount of normal stress, but the shear stress is the largest. Later on we have several failure models. One is the maximum shear stress model. So it's important to know what's the shear stress a material is carrying, because later on for some model they use shear stress as the key parameter to determine whether the material is going to fail or not. Okay? So obviously you guys know about this because everyone is very quiet. Okay, so once you can make a proper drawing of the Mohr circle, you know how to compute for principal stress 1, principal stress 2, and maximum shear stress. It's just math. Okay? So the equations are here. Okay. Now, in this particular example, on the left, along the y direction, there is no normal stress. So to make this problem more general, I've shown a different example where we have some compression along the y-axis. So the Mohr circle it has more terms. So basically the B point has some value on the normal stress. So compared to the previous case, at the B point there's no normal stress, so the equations are like simpler. But for this more general case, you can see more terms, but exactly same concept. Okay, so I will ask you to practice this back home. Okay, please do it. Because for the first exam, I will do exactly something like this. I will ask you to compute for the principal stresses, maximum shear stress. Okay? So please go practice. If you would like to memorize the equations and then apply, no problem. I don't mind. Okay? Oh, the notes will be online, so it's okay. You don't need to take a picture. And also, the TA will post the video to YouTube. So everyone is recorded. Everything is recorded. This is for future. But just quickly remind you, there's an extreme, not extreme, a special case where we are doing a tensile test. Later on, when we introduce some of the design models, this concept will come up again. So let me talk about this right now. And I know for some students, sometimes when I introduce the design equations in the future, I remind them, hey, we talk about this when we talk about Mohr circle. They forget. Okay, so now is the time for you to pay attention, because this is good for the future. Okay, you have learned the Mohr circle analysis in the past, correct? But this concept is going to be useful for later on. Remember this. This is a general force diagram for tensile test, right? So only normal stress along particular axis. And if you draw a Mohr circle, it's gonna be like this. So the first principal stress is your sigma A. And your second principal stress is gonna be 0, right? Because if you study the point right here, no stress. So if you think about it, yes, exactly. And for tensile test, if you gradually enlarge the force being applied on the material, sigma A gradually increase. So it's increasing. So that means this Mohr circle is getting larger and larger as you enlarge the force you apply. At a certain point, right here, when your sigma A equals to sigma S1 equals to sigma Y, the yielding strength, your material is about to yield. And that's the limit for your design. So later on, when we design for something, we are going to generate, formulate certain equations. It's going to use this concept. It's going to, okay, it's gonna recall the concept right here and say, hey, what's the stress for tensile test? So there will be a certain equation. And then let's start to enlarge the value. And what's the limit? Okay, the limit is gonna be the sigma Y. So this concept is the key for future derivation. Okay, so please remember this. Not important right now. Not important for the first exam. but it is important for later derivation when we talk about failure. Okay, this is for a more general case where you have how many more circles are there? So actually there are 3 more circles. So usually when we have a planar problem, we are dealing with stress along the XY plane. So you have stress 1 and stress 2. So it's like you are studying the big black Mohr circle. But if you insist to analyze the Mohr circle along XZ plane and YZ plane, you can also formulate Mohr circles. And it turns out the Mohr circles will be something like this, two smaller ones. They can be drawn in one particular drawing. So that each Mohr circle represents one planar stress analysis along a particular plane. Okay, so this is just for you to know. Okay? Okay, now the most troublesome part for today's lecture. Do we have time? Let me see if I want to move this to tomorrow. Let me see, what is this? What is tomorrow? Tomorrow is problem solving. So the slide number 2 right here is related to the problem that we're going to solve tomorrow. So, yeah. Yeah. I know. So, I'm thinking about, should I talk about this right now or tomorrow? What do you think? Everyone okay for today? Any questions? Everything is easy, right? Only today is easy. Only today. This is just to remind you, hey, you learned this in the past. Let me give you a hint about what's gonna happen later on when we talk about the design equations. Just give you a quick review, quick preview. So like this is for see, this is like the tensor test thingy that we talk about. This one is easy, so I'm not going to talk about this one. This model is the easiest. The second model is a little difficult. Second model, this one. So why people use design equations? They are looking for certain equation that has a limit. So when they choose design parameters, they know what's the limit. But how do you define a limit? They use the idea of allowable stress. Allowable stress. So later on, it's going to be a lot of math like this. And this is a model based on strain energy. In order to derive a model based on strain energy, you need to know certain general equations from stress analysis and, for example, also Hooke laws, and then what's the strain energy for elastic materials, and continue to derive. Eventually, you will end up with certain term, and you figure out what's the limit for that term, and at the end, come up with some kind of equation. So if you take a look at this equation, it tells you you can design a material, but the principal stresses along the 3 principal coordinates has to be
formed in a certain way so that the left hand side has to be smaller than the right hand side. That's it. That's the design equation. If your design ends up with some term right here on the left that is too large, so the left hand side is going to be larger than the right, then the material yields. So that's why the first couple lectures is important, because it's a fundamental knowledge for what we're going to face later on. And we can even make a drawing of this monster. Yeah. And then apply concept of safety factor. Yeah. And then apply this equation into a problem. And then you can even solve for, okay, for this particular design, now what's my safety factor? 1.44, what does it mean? My design now is 1.44 times safer than the extreme case. If the safety factor equals to 1, that means my strength equals to the stress, exactly the same. So my material is about to yield. But if I have a design having a safety factor larger than 1, then I have some margin. I am 1.44 more times than critical. So the goal is for that design safety factor. Okay? So just for you to, just a quick preview so you know, okay, it's time to study. Because the equations accumulate quite quickly as the lecture goes by. Okay? Let's get back to today's lecture. Let's get back to the calendar. I think we're only the first lecture, so I don't want to just make you hate the course. Okay, so we are done with today, this one. We will be doing the problem that I want to introduce tomorrow. Then we will be doing an exercise, truly solving some problems. Okay? Then next Wednesday, there is an exam. Next Wednesday. Since the exam is only 1 hour long, so I cannot give you something too crazy. I think I will at least, I can give you a hint about what I'm going to give you. I think I will, let's see, today's, I will at least ask you to solve for these. I may give you a force diagram, and then, hey, what's the principal stresses, what's the maximum shear stress? So at least you practice Mohr circle. Okay, so exam 1, there will be Mohr circle. Okay? So I'm supposed to give you a problem based on tomorrow's lecture. But this problem is always taking a long time to solve. Because the next problem is to draw the shear and moment diagram. This is always taking a long time. I will try. I really want to put this in the exam, but you can never finish it within 1 hour. It never happened. So probably I will give you a much simpler problem in the exam, and maybe the problem is like a problem with certain portion being given already. So you only need to do something. Okay. So anyway, this is for tomorrow, and in the exam one, I will try to ask you to solve a simplified Bing problem. Okay. So in the Bing problem, what the Bing problem is about? Usually, you first need to calculate for the reaction forces first, and then you need to calculate for the shear and moment diagram. And then you figure out where has the maximum moment. You figure out where the position is. Then you will do more circle analysis right there. At this maximum, because maximum moment is basically M, right? You need to know what would be the maximum stress due to the maximum moment. So usually the order is like this. You know the moment at certain point, right somewhere at the beam, and then you know where due to that max moment, you figure out what's the max stress. So usually the problem is about finding the location of max stress. So you need more circle, principal stresses, figure out the orientation and stuff. So once you have maximum stress at that particular point, what's next? Design equation. So usually in the past, when I give a Bing problem like this, basically giving you a problem is easy. Just change the geometry. This is a bearing, this is a pulley. Just change the orientation and then ask you to solve it. So I can create infinite number of these equations, but and just always ask you to solve for the same thing. But no matter what I do, the process of doing these takes some time, usually 2 hours. So that's what, like I said, this year I will try to figure out how to give you a much simpler version, so you don't need to solve for everything, but I want you to practice for this. This is important. Okay? So at least you know what the problem is about. And in tomorrow's lecture, I will solve for the Bing problem. And also in Dr. Patel's exercise practice next week, he will also share more problems. Okay? And I will recommend you in the exercise, when you solve it, you solve it by hand with him. Okay? So you will check whether you know about certain parts, and then you can see what he did on the board. Okay, so I think I will stop right here today. Does anyone has any questions? Yeah, go ahead.
Do we have to memorize all the formulas, or?
For the exams, I usually give you the necessary equations somewhere printed on the exam sheet, but I usually scramble them, and I don't give you any comments about which symbol represent what. I just give you, I can show you one of the example sheet in the past. So if I see if I have it here, lecture notes. Exam. This is even handwritten. Did I? In this particular one, this is handwritten, and you can see equation. You only need this. So anything else, I want you to memorize it. So this is only one particular example of the whole exam. Maybe I should show you maybe exam 2, because like this particular one. Blah, 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 this is a problem, and then hey, I show some equations. I just write it down there, and then if you didn't do your homework, then you may not know what those equations are about. Okay, and do I always give you exam sheet by handwritten? No, because I'm too busy. Sometimes I just write it down. Sometimes I just use computers, or sometimes I just bring up some of the old files and change a little bit. So you never know what I'm going to do for the semester. I even don't know what I'm going to do for the semester. So I'm sorry, I'm very random. But I will make sure you learn what's necessary for the course. Okay? And my teaching philosophy is that I don't want you to be equation memorizer. Can you say that? I don't want you to just memorize stuff and then do it. I want you to truly understand it and being able to apply it. Yeah, that's my philosophy. Because I'm very poor on memorizing stuff as well. That's why I don't want my student to memorize things. Yeah. So I enjoy exams with the equation sheet. I hate exams without the exam sheet. That's why I hate thermodynamics. Yeah. Because in thermodynamics, the equations are too easy. So giving you the equations are like giving you full credits. So it turns out they ask you to memorize it. But I hate memorizing. Okay, anyway, that's it for the day. If you have questions, you can come up or you can just leave. When you leave, please stay quiet because some other courses are still going. Okay? Did everyone did the roll call? This is the one, right? Okay, if you haven't done it, please do it. It's 1 point, I think. It's 0.5 points. Remember to do it.